we would like to be able to find the area underneath a curve, which is not a regular geometry shape. I mean, we know how to find the shapes of squares and circles and rectangles and trapezoids and all that kind of stuff, right? But if you're looking at this curved shape here and you wanted to know the area underneath that, we don't have a formula for that. So generally, the way we started is, let's just divide up that space into a bunch of rectangles, because we do know the formula for the area of a rectangle, and let's calculate the area of all of those, and we'll add it up. Now, will that be the area under the curve? No, I mean, it's an approximation. If you see this one, the way it's drawn, you can see that this little piece up there, that's not included in the rectangles. Neither is this piece, neither is this, or this, or this. Okay, so it's missing all that, not going to be accurate. Okay, what if I increase the number of rectangles, right? If I doubled the number of rectangles, then each one would be thinner, and it would be able to cover a little bit more of that space that I'm not covering now. Right? If I go from 5 to 10, there's 5 there now. If I go to 10, it'll be a little bit better. If I go from 10 to 20, even a little bit better. Right? The more rectangles, the better. The more rectangles I get, the smaller the width of any one of them. The limit of all that would be, going towards infinity. Could I ever let the width of a rectangle become 0? Because what would be the area of a rectangle if it had a width of 0? They'd all be 0, right? And they wouldn't add up to anything. Generally, the way you add up the area of all those rectangles, you just use summation notation. I equals 1 to n, length times width for every one of them, and you add them up. Okay. So the first slide was what they call the tangent line problem. That's section 12.3. This is about the area problem. That's section 12.5. I think I can just add it on here. So in order to find the slope of the tangent line, we need to know the limiting value of the slope as h approaches 0, right? As I let those 2 points come together, right, it might have a limiting value, right? If it does, then that would be the slope at that point. Right? That will be a thing that we call, you take a limit as h approaches 0 of f of x plus h minus f of x over h. Right? In order to find the area of the curve, under the curve, we need to know the limiting value of the sum of the areas of the rectangles as the number of rectangles increases, right? And, we'll let it go as towards infinity, the number of rectangles, which we know means that each rectangle is getting infinitely thin, but it's not 0. And we'll see whether those areas that we get when we add up all the rectangles seem like they're approaching some value. So that would be the limit as n goes to infinity of the sum of I equals 1 to n of L, I, W, I. So what we're doing with limits is we're going to have to do 2 different kinds of limits in this chapter. The first is when you take the limit as h, or a variable, approaches a fixed number like 0. Right? That's the first 2 sections. And then we're going to have to do limits as n, usually n, approaches infinity. Right? There's 2 different ways, you don't deal with them the same way. So 2 different kinds of limits. This limit, that leads to what's called the derivative in calculus. That limit, that leads to what's called the integral in calculus. And when you get to calculus, you're going to spend half the time here and half the time here.